Hi, this is Mike McGinn, your instructor for NetI 105. And today we are going to talk about Chapter 10, Application Layer in your NetACAD curriculum. What we're going to start out with is just kind of talking about the application layer in general. At 10.1.1.1 in your curriculum, you'll see a diagram here, and the application layer in this chapter is in reference to the TCP/IP model, which encompasses the top three layers of the OSI model, layers 5, 6, and 7. And so what we're going to talk about in this chapter is really just what applications are typically found in the application layer. First, we're going to talk about the application layer itself, which is the top layer. These are uh, applications or types of applications that are found at the very top level. Examples are DNS resolution, hypertext transfer protocol, which obviously you may know as HTTP, simple mail transfer protocol, or SMTP, which is how our emails come and go out of our email clients, whether you use Outlook or something like that. POP, or Post Office Protocol, is another example. Again, used by software that functions as an email client on your computer. DHCP, which is the protocol that is used to assign IP addresses to our clients, which we've talked about previously in the course. File Transfer Protocol, which is a protocol that is used to bulk transfer files from one host to another. And IMAP, which again is another more secure email protocol that is commonly used by email clients. The presentation layer is really kind of like the middleman between the application layer and the session layer as it pertains mostly to graphics, which is, there go, the presentation layer in the OSI model. Formats such as QuickTime, MPEG, GIF, JPEG, PNG, those are all pretty much presentation layers. So what the presentation layer does is it formats, presents data from the source device to a compatible form for receipt by the destination device. And it compresses the data and it encrypts it for transmission if necessary. So that the graphics data can or motion picture data can get where it needs to go. So the session layer, as the name implies, functions to create and maintain dialogues between source and destination. Let me back up here. So it does kind of do a little bit what the transport layer does with UDP and TCP protocols, but the session layer can also basically is a layer that maintains communication between the source and the destination applications. A lot of error correction and error handling is handled in the session layer. So it's not really covered too heavily in the chapter, but that is the fifth layer. So again, as data is, when you're sitting in front of your computer, just as a quick review, as you are as you are doing activities that require communications with a remote, host, the data is basically being sent down through the application layer, handed off to the transport layer, which is then encapsulated into packets in the network layer, frames into the data link layer, and then put on the actual data communications media. And then when it comes back, when it gets to the destination, it travels up the stack so that you actually see the response to whatever communications you've initiated with a remote host. So again, application layer, what you need to do here in 10.1.1.4 is press the button, review the various different protocols. And one thing to mention is there's a file transfer protocol, and there's also what is called trivial financial protocol. Big difference between these is one is best effort unacknowledged file for delivery, which is TFTP. Uses less overhead than regular FTP, so that's the real difference there that you need to know. IMAP is an email protocol that enables a client to access email stored on a mail server, and it maintains the email on the server, whereas POP and SMTP is kind of just a way that email client can retrieve email from a server that's email server that where email is being held for them. And also be able to send outgoing email through a server with SMTP to be able to begin the routing of mail to its final destination. POP, same thing, only it's for inbound retrieval of email. Downloads email from the server to help server to the desktop. So SMTP is really for sending mail. POP is for receiving mail. The big thing to know, you should know, to what extent it's tested, I don't know. SMTP and POP are basically clear text protocols. So as your email is flying through the internet, it's basically going through in clear text. So if you are using a POP service or an SMTP service, you know, the content of your message isn't necessarily encrypted. So that's something to be aware of. IMAP as well is not ideally secure. Protocols, proprietary email protocols such as HTTP over RDP, HTTPS, etc., are a little bit more secure for email. Platforms such as Microsoft Exchange, if you're communicating between Microsoft Exchange servers, which are email platforms that Microsoft promotes, you're at least as long as you're in the Exchange world, your data between the server platform and your client is 100% secure, or at least as 100% secure as the NSA will allow, so to speak. So, you know, what we do here in this in 10.1.1.5 is an activity to kind of map where the various protocols and standards go in the OSI model as well as in the TCP IP model in the application layer. So this is something you want to kind of drill yourself on so that as you get questions on the exam, you have a general idea of where these particular protocols and standards live. So they talk a little bit about peer-to-peer networks, and you know, peer-to-peer networking is basically if you got a little network in your house, or even if a small business may have a peer-to-peer network, basically every device is considered equal in the communication process. You don't have a central server that is generally controlling the network for as far as network services and things like that. A lot of times you have like a router that's providing DHCP and is forwarding DNS queries to a DNS server out on the internet. But peer-to-peer networks obviously require 2 or more computers and can share some resources, whether they be printers or files, without having a dedicated server. Every device is known as a peer, and so one computer may assume the role of a server for a particular transaction while also serving as a client for another. So that means that you may have a share on your computer that you use for whatever you need your computer for, and it is also a common resource for other clients on the network. So what we have is there are some peer-to-peer applications. A lot of messaging software like instant messaging is a peer-to-peer application. So that's the most common example that you might run into. They list a lot of other different protocols that are point-to-point. Some of them you may be familiar with. A lot of these are pretty obscure, but there are peer-to-peer applications that are out there that just allows one computer to talk to another. They're mostly in the messaging area. Then we talk about the client-server model, and this is different. This is where you have a centralized server that generally is a resource for all the clients on the network for resources such as file storage, print serving, etc. So you have a server on the hardware side. You have a server, and then you have various different clients, whether it be a phone, smartphone, or a PC. So what happens is the server downloads data at the request of the client, and the client puts data up to the server in the form of an upload. So your well-known application layer protocols and services are, HTTP, which is what a lot of web applications are developed in. Simple mail transfer, SMTP, simple mail transfer protocol, and post office protocol, or POP. So they make it possible to browse the web and send and receive email, etc. So a lot of this stuff that you've probably been aware of before, but you're sending a request for a page with HTTP. The website responds with basically a script of HTTP language, of which your web browser then can translate into graphic images. So that's kind of what's going on with HTTP. With also HTTP, the specific request is a GET request. In the HTTP language, for example, getting a particular website based on a flood qualified domain name, as they show in this illustration. And then the SMTP protocol is what's sending email to this mail server, and POP is what's receiving the email. So how does that work between different emails if you're sending to a domain to another, a mail recipient on a different domain? This illustrates kind of what's going on with that. The sending of mail, it goes through the internet to your home SMTP server, and then through your ISP, and then it gets routed to the mail server of the other ISP, of which then is pulled through POP to the particular recipient, or by IMAP. So a little more description on SMTP and POP, a little more detail. This isn't tested too much, but the MTA, or the mail transfer agent, is a process that governs email handling between servers and clients. So the mail server is going to have some sort of a program that's managing all of this, which is generally an application that it has got some services running. It's looking for messages from SMTP messages as well as POP3 requests. So they go into a little bit of detail on SMTP and POP and IMAP and how those all actually work. Again, the mechanics of this aren't tested, but this is just good general knowledge for you to understand. So DNS. DNS is something that I am surprised how many people don't really understand how DNS works. It's really probably one of the most important applications for internet or even internal network clients. DNS is basically a bunch of servers on the internet that are considered root servers, and what these do is these are large databases that map DNS names to specific IP addresses. For example, www.cisco.com is a website. Well, in order for you to get to that website, you have to utilize a DNS server. So what happens is the client is going to query a DNS server to get a translation of www.cisco.com to an IP address of 198.133.219.25. So the DNS server basically queries and gets that information and then sends the IP address back, and the client then gets that address and then can communicate with that in the website to pull the page. So a DNS server has, like I said, it's a database, and different types of information has different types of record types. So for example, an A record is an end device address. So for example, if you're on a local area network where you're logging into a domain, your end device that you're using will very likely be automatically updating a DNS server. And since you're a host in that domain, you are having an A record created on the DNS server, which is what we know as a host record or end device record. An NS record means that in a domain, like a Microsoft domain, it means that it says that this particular name server is authoritative for that particular domain. So your DNS servers that are on your local area network are authoritative for your local domain, whereas it is not authoritative for, say, a domain somewhere out on the internet. A CNAME is kind of like an alias. It's a canonical name or a full qualified domain name for an alias used where multiple services have a single network address. So for example, if you can refer to a particular website as, let's say Ford Motors, motorcompany.com might resolve to the same website as Ford.com or F150.com. All those three fully qualified domain names could end up resolving to the same actual physical host with one IP address. That's where the CNAME comes in. And the MX record in a DNS database is really telling for a given domain how do you get to the actual mail server that is authoritative for that domain. So for example, a host, let's say mail.ford.com, is basically an MX record that tells a particular client or a email client how to go about getting the IP address to send that message via SMTP or otherwise. DNS, the thing that's cool about DNS is that it's very scalable. You've got a DNS client, which might be your PC. It can go to a local DNS server to do local resolution, as well as cached information about external websites. And what we mean by cached is that most DNS servers, when they go and they have to query DNS servers, authoritative DNS servers, or root DNS servers out on the internet, it will keep that resolution on your local DNS server for a certain period of time, which is called caching. Where this is beneficial is that it speeds up how fast you can resolve your queries locally to IP addresses. In other words, if somebody in your organization has already queried Ford.com, but that first time they did that, it had to go out and had to resolve all of that all the way to the root server. That took a little bit of time. So what it does is it keeps that entry cached on your local server so that the next time you got to get to, well, in this example, Cisco.com, you can retrieve that IP address for your DNS client very quickly because it never has to go out and do a requery out to the outside servers. So this graphic does a good job of explaining the hierarchy of DNS servers and how that all works. So again, just to summarize, if a DNS server client, say you're on a web browser and you want to query Cisco.com, go to Cisco.com, it'll go to the local DNS server and it'll look in the cache. And if it says it's there, great, it just gives you the IP address right back. If it doesn't have it, then what it does is it sends a DNS query out to the top level domain servers to see if they have them, which if they don't, then those in turn will query the root DNS servers. That's why when you make a DNS change, like an IP address change for a website or something like that, you have to change your authoritative DNS servers, and then they have to replicate through the internet. So you generally need to leave yourself 24 to 48 hours when you change the public IP mapping to a particular DNS name. NSLookup is a tool that basically will tell you what the authoritative name server is, or how it gets its resolution for a particular address. The NSLookup is a command that is issued. The default DNS server configured for your particular device is displayed in the example, and the DNS server in this example is DNS-sj-cisco.com, which has an address of 171.70.168.183. The name of a host or domain can also be entered into the NSLookup prompt. In the first query in the figure, a query is made to say Cisco.com, and the responding name server provides the address of 198.133.219.25. So basically, the server that answered that query is displayed in that example. There's a lot of options in here that aren't really covered, but in the NSLookup utility, you type in NSLookup and you can get right into the NS command line, and then to exit, you hit the exit prompt. So there's a syntax checker exercise that you can go through on that. That's a very handy utility. I use it fairly regularly in my travels on work that I do. Next, we're going to talk about DHCP. DHCP, again, is what basically tells a DHCP client what IP am I going to use for this particular session. So this, when you boot up a computer. And so we go through what the DHCP operation. And what DHCP does is it sends a series of messages to basically do the communications with the DHCP server. First message for a DHCP client when you cold boot it is it says, hey, I need an IP address because I'm a DHCP client. And so it sends out a broadcast DHCP discover message to go and find a DHCP server on that particular IP segment that is authorized to answer DHCP requests. And then the DHCP server says, hey, I'm a DHCP server. You want to use me? And then the DHCP client says, yeah, give me an IP. And then the DHCP server says, okay, here you go. So that's in a nutshell what's going on with DHCP protocol. So there's a packet tracer on DHCP and DNS servers. Good exercise to go through there, and also a lab as far as observing DNS resolution. I'm not sure if this is in the net labs or not. I'd have to go look. It might be one that's always required is your own computer to be able to go through that lab. And then they talk about in a little more detail what FTP is. You can kind of go through that. FTP gets used fairly regularly. A lot of times it's behind the scenes of a FTP client. FileZilla is one that's very commonly used, and there's a lab on that. And then SMB is a protocol that's used for file sharing. A lot of file servers use this, and they talk about that as well. So that's really all there is in the application chapter 10. I can tell you it's not tested real heavily. I think what I would focus on is that graphic that we did earlier. Let me see if I can find it real quick. I think, making sure that you know what layers in the OSI model map to the TCP IP model application layer, that's important. And basically knowing what each protocol is generally used for. So this is knowing what these protocols are used for, where they go in the OSI model. I would make sure you're brushed up on that. And then really knowing what all these protocols are actually used for. You should know that POP is a mail protocol basically for receiving email. You should know TFTP is a best effort file transfer protocol. You should know that FTP is a connection-oriented file transfer protocol. Things like that. And I think if you get those down, that's good. The other thing I would know is I would understand DNS resolution, DNS record types, know about the NS lookup command, and be comfortable with how you can do some of the basic things there, and knowing the DHCP operation in terms of what's going on between DHCP server and client. Not only when you first boot up a computer, but one thing a DHCP client gets is it gets a lease. So when it does get an IP address, it's only good for usually about 8 days, unless it's configured otherwise. So what happens when that lease expires, and that sort of thing. So those are all things that either are going to be tested on or should just be committed to your general knowledge about how networks work. So that's all I got on this session. I appreciate your time, and I think we only got one more of these, if I'm not mistaken. So be ready for the chapter 11 overview here real soon. See you soon. Bye.